We're going to talk about trigonometry identities, and trigonometry identities really helps an individual to solve problems pertaining to advanced mathematics when you come to calculus 1, calculus 2, so on and so forth. Because like when you come to certain areas in calculus, you need the knowledge of trigonometry to solve certain problems. So we're going to show you what are some of the main identities that are used in solving a problem. Now, some of these identities came as a result of one theorem which is very powerful, and then it is not new to us, which is the Pythagoras theorem. And that Pythagoras theorem can be applied using a right angle triangle. Let's say you are given a right angle triangle here, and this right angle triangle is given as A, we call this side B, and C. Then we have our 90 degree here. Okay, then we know that the direction where the 90 degree is facing is where we look at our hypotenuse. Okay, so we have our hypotenuse here, but the opposite and the adjacent depend on where the angle is facing, the direction in which the other angle is facing, excluding the 90 degree. Let's say I put my angle here, theta. It can be an acute angle or any other angle other than 90 degree. Okay, I put my acute here, my angle here at C, which is theta. Now this angle will determine the direction where the opposite will be and where the adjacent will be. Many times people confuse themselves always that whenever you have a right angle triangle, this other side is the opposite. That is not the case. It's the angle that determines where the opposite will be and where will the adjacent will be. Now if you observe, this theta here is facing the length of AB, then AB is the opposite of the angle. So here we call this one the opposite. Okay, the shortcut of opposite, I just put there OPP, and then again where the angle is sitting on is what we call the adjacent, meaning the leg of the angle there. So this side is the adjacent. People should be very careful of that. What of now I happen to draw another right angle triangle, okay, and I indicate my 90 degree here. I put this angle here as alpha, and then I label this as M, N, and P. So remember that the angle, the opposite is always determining the direction where the angle is facing. If you observe here, this alpha is facing the direction of what? MP. So meaning this MP is the opposite of the angle. And then NP is the hypotenuse, NP is the opposite, then automatically MN is the adjacent. Here will be the hypotenuse because 90 degrees facing that side, and then the angle alpha here is facing the line of NP, which is the opposite of that angle, and then we have MN is the adjacent of the angle. So these are some of the basic things one need to know in order to prove the trigonometry ratios. Okay, now what are some of these things that we need to show here today? First of all, if you observe that there's a right angle triangle as we discussed previously, we have our 90 degree here, we call this one as A, we have our B, and our C, we have our angle here, theta, then we know that this is the opposite, okay, the opposite, the adjacent. Equals to the opposite square plus the adjacent square. Or since there is an addition sign between the opposite and the adjacent, meaning they are commutative, the arrangement does not matter. You can either start with the adjacent square plus the opposite square, or the opposite square plus the adjacent square. The arrangement does not matter, vice versa. So this is what the Pythagoras theorem is telling us. How can we derive here some relation? We use very important slogan that we are always familiar with, and that slogan is what? SOHCAHTOA. We say using SOHCAHTOA, where each one of these things is representing something. Okay, from this right angle triangle. This S is representing sine of the angle. You have sine. What is the angle there? Is theta. You have sine theta is equal to. This O is representing the opposite. I will abbreviate it as OPP all over. The H is representing the hypotenuse. We have HYP. That's for the sine. Meaning sine is always equal to the opposite all over the hypotenuse. Now let's come to the second one, which is CA. we have cos of the angle, cos theta, our area is representing the adjacent, and then our height is representing the hypotenuse. So we have adjacent all over hypotenuse. Okay? Then we also have the tan, which is the toa, opposite tan of the angle is opposite all over adjacent. Good. Now from here we can use this Pythagorean theorem in order to find ratios, trigonometric identities that will help one or an individual to solve problems related to trigonometry. Okay, what we're going to do here is we're going to take this relation, which is what? We have hypotenuse squared is equals to opposite square plus the adjacent square. Now what will I do here? First of all, I have to divide everything by this hypotenuse square throughout the equation. Okay? And that is to see now have hypotenuse square divided by hypotenuse square. Okay, this one again by hypotenuse square. Hypotenuse square divided by hypotenuse square, that's automatically 1 is equals to, we have opposite square, okay, we have opposite square all over hypotenuse square plus adjacent square all over hypotenuse square. Good. Now going back to the relation that we have already established earlier on, we see clearly that sine is the same as opposite all over hypotenuse. And if you observe from this relation what we have tried already, we have seen that we have opposite all over hypotenuse and all of them are in square. Here you can apply the laws of indices so that you can put them in one bracket and raise it to the power 2. So this is the same as 1 is equals to, open our bracket, we have opposite all over hypotenuse whole square. We have plus, open our bracket again, we have adjacent all over hypotenuse whole square. Now vividly we can see a clear picture that there is something happening. If you observe here, sine is the same as opposite all over hypotenuse. We also have here opposite all over hypotenuse. We can represent it as sine of the angle. Which angle? Angle theta. So we say 1 is equals to, we open our bracket, we have sine theta whole square. Since all of this is having a square, we have plus again, open our bracket. And if you check, we have here adjacent all over hypotenuse. Going back to the ratios here, we know that there is one of the ratios which is having adjacent all over hypotenuse, and that is cos theta. So cos theta, we represent it as what? This adjacent all over hypotenuse represented as cos theta whole square. Now, here again, one has to be very careful. This sine theta squared plus cos theta squared simply means that this sine theta squared is, this square is affecting the function. It has nothing to do with the angle. This is not equals to. When you see, note, when you have sine theta whole square, this is equals to sine square theta. That simply shows that it is affecting one of the functions and it is not affecting the angle, and it is not equals to sine theta squared. This expression is not equal to this. If you do this, this simply shows that it has nothing to do with the function, but it is only affecting the angle. So these are some of the things one needs to take note of whenever you are dealing with trigonometric ratios. They are very important things. Now moving on here, we can represent this as what? Sine square theta. So we have now therefore 1 is equals to sine square theta plus cos square theta. And this is one of the first trigonometric ratios for the identities. This is a very common identity as trigonometry is concerned. Okay, and from this identity you can derive other identities as well. Let's say I happen to divide both sides by sine again. From this equation we have our first identity, which is sine square theta plus cos square theta is equals to 1. Oh, one can say 1 is equals to cos square theta plus sine square theta will always give you 1. So from this identity you can derive another identities.